Hey guys, we're going to get started. Sorry to miss class today, or maybe it's you that's missing class, either way. But I'm going to go over and go ahead and have you record the notes that we did on the Black Day. Okay, so the first two people that we're going to talk about is Aristotle and Democritus. So both of them were back in BC. Aristotle was the first one that we're going to talk about, a philosopher at that time, as was Democritus. And what Aristotle said was that everything was composed of earth, fire, wind, and water. And so although he was very generic in his description, if you watched your Edpuzzle videos and so forth, we know that he is somewhat correct in that everything is made up of those four substances. The second person was Democritus, again, in the BC area. And he was actually the first person to come up with the concept of an atom, that there being a possible substance called an atom. Some of the things that he did say, though, that atoms were the smallest individual structure known to man. And the key here that he was wrong about, but at least he was in the ballpark, was he said that they are unable to be broken down into smaller substances. And so he was wrong about that, even though he was starting off at least thinking about the atom. So we now know that we have what we call subatomic particles. So those are the two people that we're going to start off, which were BC. Okay. So now we're going to take a big jump. We're going to go to 1803. And the guy we're going to start talking about was John Dalton. And John Dalton is known for what we call the solid sphere model. So he began the first model of the atom. And so it did look like a solid sphere. He just thought it was just like a hard ball, a solid sphere. So here's what he said. Atoms were small, hard spheres. Atoms of a particular element were identical. And atoms combined to make compounds. And then he was the first to use symbols for elements. Now let's back up before you start taking notes. So one of the things, atoms were small, hard spheres. Well, that part, of course, is not correct, and we'll find that out later on. But one thing he was correct about, so every person had kind of their area that they were true about. His was that atoms of a particular element were identical. And so what we're talking about that is that if you have a hydrogen atom, okay, let's say hydrogen atom, then all hydrogen atoms are somewhat going to look exactly the same. They're not going to look like a helium atom. Okay, now the only thing that he was a little bit wrong on this is we have now found that we have things which are called isotopes. And we're going to talk more about isotopes and actually be able to calculate those. But isotopes are simply the hydrogen atom that may have different numbers of neutrons. So one hydrogen atom may have 0 neutrons, where another hydrogen atom may have 1 neutron or 2. So there's slightly difference just in the fact that their mass is going to be different. But for the most part, they're going to look the same. They're going to act the same. They're going to interact at that point the same. So that's where John Dalton was correct. The other thing that was really interesting was he was the first one to start using the symbols that we now have today. And of course, he only had symbols for what was the known elements at that time. So we've got John Dalton as being our first person and the solid sphere model. Okay, so the next guy that we're going to talk about is J Thompson. He was in 1897, so about 90 years past Dalton. And he has what we call the plum pudding model. Now, if you watch the video, they've changed it from plum pudding to chocolate chip model. And I think the reason being is that because people don't eat plum pudding much anymore. So a lot of people don't know what the plum pudding model would mean. And so we call it the chocolate chip. I kind of call it the chocolate chip with some nuts in it model. But basically what we're talking about is, again, he's still kind of going on Dalton's solid sphere model, but now he's saying that inside that solid sphere, we have positive and negative charges that are just kind of floating around inside there. And so, again, that's kind of where that chocolate chip model comes in at. So this is what his model looks like. So if you had to pick out and or draw his model, this is what we would see. Okay, so let's talk about some of the other things that Thomson discovered. So he was the main discoverer of the electron. He didn't call them electrons at that time. He called them corpuscles, which I think is, I'm kind of glad they changed the word from corpuscles to electrons. A little bit nicer sounding. So up here where we were talking about the fact that Democritus didn't think that we could break things down any smaller, we now have Thomson who said, yes, we can. We now do have subatomic particles. And so he was very aware of the electron. And then he also found that the electron had a negative charge. So let's talk about how Thomson did that. And he did that with our cathode ray tube. Okay, so if you'll remember from the video, what he showed was that he had this tube and it had this bright green shining light because it was a beam of electrons that he was shooting through. So this negatively charged beam is shining through this cathode ray tube. And so what he does then is he takes a magnet and he puts that magnet up beside that light to observe what happens. So first off, when he put the negative charge of the magnet up beside the electron there, it repelled it. Okay, now at this time, he doesn't really know that this is negatively charged. He just knows he's shining a beam or shooting a beam of electrons through. He doesn't know that it's negative. But when he puts that negative magnet on there, we do know at this point in time that if you have a negative and a negative charged magnets, that they repel. And that is exactly what happened. So when he put this magnet up here, it took this beam and it repelled it. Okay, it pushed it away from. And so again, when he placed a negative magnet, it repelled. Okay. And then the next thing that he did is that he placed a positive into the magnet. So we'll put the positive in here. And when he put the positive in to the beam that was coming through here, it attracted it, okay? And so it attracted the beam. And so from that, he could conclude that this electron beam that he was shooting through there had to be negative, because for the fact that we know if I have a negative and a negative, it will repel, or light charges repel where opposites attract. That's the and symbol, okay? So because of what we know with magnets, he was able to actually determine that that electron is in fact negative, okay? So again, you got J Thompson, chocolate chip model or the plum pudding model, whichever one you would like to call it. He discovered the electrons and he figured out that the electron had a negative charge. Okay, the next person that we're going to talk about is Rutherford. And Rutherford did what we call the nuclear model, okay? And his thing that he's really known for is the gold foil experiment. So let's just look at that experiment before we do too many notes. So this is Rutherford's gold foil experiment on there, if you can look at the pictures here. So this was J Thompson's plum pudding model. And so what Rutherford did is that he fired positively charged alpha particles, okay, at this thin gold foil. And he was thinking that things would look like this. So what he expected to happen was for everything to just go through, okay? So he said everything should have been able to just pass through without being deflected, okay? That's what he said. So this was what his hypothesis was that he thought was going to happen. But in fact, what happened was when he was shooting those alpha particles in, a lot of them did just go right through, okay? But you also had some that obviously hit something and bounced completely back, okay? They bounced back. Or maybe they were deflected out to the side, okay? And then again, this is the picture of the setup of it. So what he was able to conclude was because of the fact that these things were bouncing back. Okay, we had these that were bouncing back or being deflected off. And if you watch the video, then they were doing a counter on there, and they were showing that, it was something like 1 million, or, let's say, particles that were able to go through. And then there was like 100 or 1,000 or something that was deflected off. Okay. And so he knew, because there wasn't that many of them, that this spot, wherever they were being deflected, it wasn't that large, but it was obviously hard enough, dense enough, that when those alpha particles hit it, it bounced them back. Okay. So what he was able to conclude then from that was that there were a positively dense core. And the reason why he said it was positive, okay, had to do with the fact that he was, again, shooting in positive particles. And so it's kind of like, again, what we just talked about, positive and negative and positive and so forth. So when that positive was coming in and it got close to that positive core, then it was bouncing back to it, because like charges repel. Okay. And so he called that the nucleus. Okay. And then he also said, well, there's got to be a lot of empty space around it. And we already knew about the electrons. So he says that nucleus is being orbited by lighter, negatively charged electrons. Okay. And he also was able to conclude that the atom was mostly empty space. So what we're talking about that is, so we kind of call his kind of like a solar system. That's why it's called the nuclear model also, because he found the nucleus. So we've got this nucleus. So if you're thinking in terms of the atom as a whole, okay, if you think of all this yellow, okay, out here where the atoms are running around, so this is a very small piece compared to the whole. So this is where he's saying this out here's got to be a lot of empty space. There's your hard, dense center. Okay. So he's getting closer to what we now know to be true. He's still got few little things off, but this is definitely a very good example of what our atom looks like. So we've now gone from that solid sphere to the plum pudding or chocolate chip model. And now we're all the way to the nuclear model. And so now we're going to do the next model. Okay, so we're going on to our next guy. This is Bohr. I believe he was in 1915, but you could always double check that number for me. But somewhere in that vicinity there, after Rutherford for sure. And his is called the Planetary Model. So very similar to Rutherford in a way, because Rutherford thought this looked like a tiny solar system. But where Bohr's differ, okay, is where Rutherford really didn't know what this looked like. He just knew that the electrons were out here somewhere. They were negatively charged particles. And he really wasn't sure what they were doing, but he kind of felt like they orbited like the planets did. Where Bohr comes in and he says, okay, we're now going to talk about energy levels. And so what Bohr realized was that there are some kind of energy levels out here, but where he was wrong was that he thought that these specific energy levels that we had, that the electrons had to be in a specific energy level. Okay. In other words, if they were in energy level 1, or they could be in energy level 2, and they could jump from level 1 to level 2, but he did not think they would ever be inside or in between. So he thought they were in very distinct levels, kind of like a track. You're going to run in lane 1, or you're going to run in lane 2, or you're going to run in lane 3. You can't run on the line or kind of zigzag back and forth. So he felt all electrons kind of stayed in their own lane. If you were in energy level 1, you were in energy level 1. If you moved to level 2, then you had to stay in level 2. So you couldn't be in between there at all. But what he did realize to be true was he said when they changed from one energy level to another energy level, they did either absorb or emit energy in the form of photons. And we now know that to 100% be true. And so when we talk about the electrons, we talk about them being in their ground state and their excited state. And we're going to come back to that in another video because we're getting too long here. So the next video, we'll talk about what our actual model is that we use today.